Good morning everyone and welcome to my YouTube channel. So here today we are going to be introducing dimensional analysis. So one thing that we need to know is, why is dimensional analysis important? So if a physicist wants to introduce a formula, they have to undergo the principle of dimensional analysis. So dimensional analysis is important for, number one, showing the validity of an equation or how correct the equation is dimensionally. Now we have talked about the dimension. Well, how can we define what a dimension is? So a dimension is defined as a physical quantity being described. So we have defined it as a dimension is a physical property that the quantity describes. Like for example, if we talk about, so let's say we are talking about the length. So these are the dimensions. We might be talking about the mass, other quantities that we might talk about, just the quantities. Let's say we are talking about velocity. So this velocity being velocity, we know that the velocity has got some length per unit time. So now we are going to describe more of this later in the video. So now, these are some of the things that dimensional analysis deals with. So dimensional analysis, we are going to be sticking with three physical quantities, or rather the properties. So for example, let's talk about the things that we'll be having are length, the time, and the mass. So this is what we are going to be sticking with. Now, sticking to these, from these we can create other dimensions. Like for example, when you say that your velocity, okay, let's begin with, let's say you are talking about distance. Distance is defined as the length per unit time, or we have just our length. So distance is length. So already, if distance is just some length from one point to another, it is still length. That's still your distance. So this one, now when we are writing dimensions in dimensional analysis, we'll be having square brackets. So this distance will take these square brackets. When we have our displacement, same principle. So displacement will also, it is also a unit of length. So as long as it's a unit of length, it shall be assigned the letter L like that. So now let's also talk about the velocity. We know that the velocity is defined as the displacement over the time. So the displacement, we know that the dimension of displacement, now displacement, by the way, is just defined as the change in position. So if you are from here to here, that means to say, let's say you were here, now you are here. It means to say your displacement is the change in position, and this one is just length. So the length from where you were to where you are. So displacement over the time. We know that the velocity is the change of displacement over the change in time. So these will be defined like that. Then the other thing that we are going to have is, let's say now, so we can simplify this by saying that already, so we have our L over, we have our time like that. So already this can be written in one bracket by saying that this is your L over T, then have one bigger bracket. Then what we are going to have is our L, so we can combine these by saying LT. So now, how do we come up with that? So this is LT raised to the power negative 1 like that. So already, y negative 1, that's how exponents are. If it is down, it can take positive. It goes up. If it goes up, it can take the negative. So these are the dimensions of velocity. Let's also define the dimensions of acceleration. So acceleration is defined as the velocity over the unit time. Now we have defined our units for velocity to be LT raised to the power negative 1 like that. Then we have our time, which is just t like that. So we can define our acceleration to be equal to the lt raised to the power negative 1, then over we have the t raised to the power 1 like that. So we have our t to the power 1. So we can combine the brackets. So we are going to have our lt raised to the power negative 1, then we have over we have our t to the power of 1 like that. So that is what we have there. So we have over our t to the power 1 like that. So we can combine now using the rules of indices. We can say that this shall be equal to L t. This one is negative 1. So in order we have t is common, we can just subtract 1. That's the meaning. T negative 1 divided by t is, this one just becomes minus 1 if you're dividing indices. So this one becomes our L. This one becomes our lt raised to the power negative 2. So this is our acceleration. So this is our acceleration like that. We can also define our force. We can also find the dimensions of our force. Our force will be assigned unique letters. So we have the force is equal to the product of the mass times the acceleration according to Newton's second law. So mass times acceleration is equal to force. So the force is equal to, we have the mass like that, then our acceleration, we know now that it is equal to L t raised to the power negative 2 like that. So this is our force should be equal to, we have our m L t raised to the power negative 2. So this is our force, or this is our force in terms of dimensions. When we look at our types of quantities, we have two types of quantities. So these quantities might take the form variables and constants. So we might take variables and constants. So when we talk about these, firstly we have the dimensional variables. So these will vary with respect to something. Like for example, the acceleration is not always like a constant thing. And it also has got units, or should I say it also has got dimensions such as lt raised to the power negative 2. We might have other things such as the velocity. These have got the dimensions and they vary, not in terms of the dimensions, like the value of the velocity. So these are dimensional variables. So we have non-dimensional variables. So the non-dimensional variables, these vary but do not have more like the dimensions. Like for example, when you look at your angle, so your angle varies. You might have an angle of 20 degrees, 70 degrees, but according to dimensional analysis, angles are considered to be dimensionless. Yes, quite alright. It is a variable, but it is not considered as a dimensional. It is not defined as a dimension. So dimensional constants, these are more like, they are constant in terms of the value, but have got dimensions. So like for example, when we talk about the gravitational constants, as you go along the way, you will find that the gravitational constant has got the value of the gravitational constant has got the value of 6.67 times 10 to the power of negative 11 like that. So this has got units of Newton meter squared kg raised to the power negative 2. So now you will realize to say this value is constant, however, but it has got dimensions. The Newton is a dimension, the meter squared and the kg like that. So now these have got units, or should we say, yeah, so these are the units. Now as long as we have that is what we are referring to as dimensional constant. Like for example, the other example that we can talk about is the speed of light in a vacuum. So the speed of light in a vacuum is equal to the speed of light in a vacuum is equal to 3 times 10 to the power of 8. This one is constant, but it has got dimensions. So these are the units, meters per second. So the dimensions are length per unit time, like that. So the other thing, so non-dimensional constants, these do not have dimensions. So they are constants, they are just defined as just mere numbers. Like for example, if you say that your 7, this does not have dimensions, your 3, or sometimes pi, which is just 3.142, and so on. Now, so finally, let's just look at what are some of the limitations of dimensional analysis. So limitations to dimensional analysis are, firstly, we have the value of the proportionality constant. Proportionality constant cannot be determined by dimensional analysis. So so the value of the proportionality constant cannot be determined by dimensional analysis. Now we said that dimensional analysis can be used to derive a formula. Like for example, if you look at your kinetic energy is equal to half mv squared. So they used dimensional analysis to come up with this. Now the question is, you might wonder, how did they get this 1 over 2? So dimensional analysis does not give you the value of these constants. This constant can only be found by experimental methods. You try out as your experiment, it's giving you a certain value. So it approached a 1 over 2. So dimensional analysis cannot give you this constant. The other limitation to dimensional analysis is that it cannot be used to derive a relation that is among physical quantities if there are more than 3. So what we simply mean by this is that firstly, under dimensional analysis, we are just going to strictly be using the mass, unless we are told otherwise, the mass, the time, and the length. So if a relation is more like the formula on how the components are related to each other, or the function. So now, if let's say a formula has got more than these dimensions, you cannot use dimensional analysis to come up with that relation. So this is what we mean when we say it cannot be used to derive a relation among physical quantities if there are more than 3 unknown variables. The unknown variables we are talking about are the mass, let's say mass, time, and length. If there are more than these, then we cannot use dimensional analysis to derive such a relation. So the other limitation to dimensional analysis is that it cannot be used to derive a relation. It cannot be used to derive a relation that involves logarithms, trigonometry, and exponentials. So what we simply mean is that, firstly, under dimensional analysis, we consider trigonometric, exponentials, and the logarithms to be dimensionless. So that's why dimensional analysis cannot be used to determine the formula having an exponential or something. Let's say that the formula is y should be equal to e to the power x. So this cannot be used to find using dimensional analysis, as exponentials are considered to be dimensionless. The other thing is that a dimensionally correct equation may not be the correct relation, may not always be the correct relation, because there are other physical quantities that may depend upon the same dimensions. So what we mean is for example, if let's say you have your torque. So the torque has got the dimensions of your mlt ml squared t raised to the power negative 2. Now the same dimensions for torque are the same dimensions for work, which is our ml squared t raised to the power negative 2. So this is as a result of, we know that torque is defined as the force times the momentum, which is just the radius from the point of axis. So now this is a distance already. We know that radius is a distance. So already whatever it will be force times the radius. Even the work done is equal to the product of the force times the distance, though the distance is in different directions, but they both, this is the distance, this is also the distance. So just because you say you get a dimensionally correct equation does not mean to say your equation is correct. So this is why. So thank you very much for watching. Hope you would like, subscribe and share for more. See you in the next tutorial.